This module was a bit different from the preceding modules, and its primary purpose was to introduce you to some bonus information on some of the subjects from the course. First, we saw that it matters how we interpret the input size. We can express the complexity of an algorithm in terms of the number of elements in the input data and get one level of hardness. And we can express the complexity in terms of the total input size measured in number of bits and obtain a possibly higher level of hardness. That is, an algorithm with a polynomial complexity in the former case may have an exponential complexity in the latter case. So when communicating complexities and when trying to understand how execution times may evolve when the input size grows, it's good to know that different input size interpretations may lead to different complexity characteristics. But don't overthink it. If you find it easier to express complexities in number of elements when considering everyday problems, then go ahead and do that. It's a perfectly valid strategy for analyzing the computational complexity of your code and algorithms. Next, we saw how problems can be categorized into complexity classes. The complexity class P covers problems that are solvable in polynomial time. The exponent may, in theory, be arbitrarily high, but theoretically oriented computer scientists still consider problems in this class as somewhat easy problems. Another complexity class, NP, only requires that the problem solutions are verifiable in polynomial time. Intuitively, this is a weaker requirement, so intuitively the hardest problems in NP should be harder than the problems in P. The NP hard problems are at least as hard as the hardest problems in NP, which were referred to as the NP complete problems. We saw a couple of examples of such NP hard problems and saw that a problem can be very simple to describe but still be incredibly hard to solve. An example is the traveling salesman problem that asks for the shortest possible route that covers all cities that a salesman has to visit. We also saw that despite that the class NP seems larger than P, it's still unknown whether this is actually the case or not. And a price of $1 million has even been set to the first that either proves or disproves that P equals NP. Last, we considered heuristics and approximation algorithms. Their general purpose are to trade accuracy or precision for computation speed. Heuristics do not promise a worst-case inaccuracy, but approximation algorithms operate with an allowed error and will produce a solution that is guaranteed to be within this allowed error. And for some approximation algorithms, the so-called p-test algorithms, the complexity and allowed error are directly coupled. So now we have seen two different approaches to define complexity. We have gone rather theoretical and discussed complexity classes and the yet unsolved P equals NP problem. And last, we saw a few different techniques for dealing with difficult problems. If you feel for it, I encourage you to try implementing an algorithm that solves one of the hard problems I presented. For example, the orthogonal packing problem, the traveling salesman problem, or the subset sum problem. It can be really eye-opening to try throwing a simple problem against a modern computer and experience how even modern and powerful hardware only tackles relatively small inputs before the execution time explodes.